Good morning, ladies and gentlemen. Welcome to the video lesson for Chapter 1, Section 6. This is the Part A notes, so the first piece of the notes for Section 1-6, which is entitled Function Operations and covers function operations and composition. So keep in mind that just like with numbers, we can add, subtract, multiply, and divide functions. The one thing you have to keep in mind is that the domain of the resulting function will be based on the domains of the first two functions. For instance, if f of x doesn't have 0 in its domain, then f plus g of x will also not have 0 in its domain. This is especially complicated when you do division. F of x divided by g of x. Remember that g of x would not be allowed to equal 0 at any point. So any x value that would result in a g of x value of 0 would have to be excluded from the domain of f divided by g of x. Now again, notice the notation there. F plus g of x is the same as f of x plus g of x. F minus g of x is f of x minus g of x. And f times g of x is f of x times g of x. And f divided by g of x is f of x divided by g of x. So please keep that in mind as we go through our first couple examples here. So example 1 says let f of x equal 4x plus 7. G of x equal the square root of x plus x. Find f plus g of x and f minus g of x. So we'll start with f plus g of x. Remember that when we see that notation, f plus g of x, that is saying we're going to take f of x and g of x and we're going to add them together. So that is as simple as us taking each of these functions and plugging them in the appropriate location. Okay? So these two expressions get plugged in here and we get 4x plus 7 plus the square root of x plus x. From there we look for anything we can simplify. In this case there is a set of like terms and we would combine those to get our final answer of 5x plus 7 plus the square root of x. Then we would consider domain. Well, the domain of this function, the 5x can be whatever x value we want. However, the square root of x has a domain that is only greater than or equal to 0. So the domain of f plus g of x would be 0 to positive infinity. For f minus g of x, we do something very similar. We do f of x, and then we subtract g of x. Now there is one slight change in the way that we do that, because when we plug these things in, we plug f of x in, we plug g of x in, the negative in front of g of x does have to affect every term of g of x. So we're looking at 4x plus 7, 4x plus 7 minus the quantity square root x plus x, which means we would distribute, and that would give us 4x plus 7 minus the square root of x minus x. So then when we combine like terms, our final function for f minus g of x would be 3x plus 7 minus the square root of x. It does not change the fact that the domain is still just the numbers that can be put underneath the square root, which would be x greater than or equal to 0, meaning the domain would be 0 to infinity, including 0. Okay, example 2 is similar, only it has multiplication and division. So when we do f times g of x, remember that means we're doing f of x times g of x. Again, overall, what we're doing is we're just plugging those values in and then evaluating. So we're plugging f of x and g of x into this expression and then multiplying it out. So we have x squared minus 9 times x plus 3, which will require us to FOIL. So we'll do x squared times x squared times 3, negative 9 times x, negative 9 times 3, to get x cubed plus 3x squared minus 9x minus 27. That cannot be simplified because none of those items are like terms. So that is our answer, x cubed plus 3x squared minus 9x minus 27. That is a cubic equation, which means there are no restrictions on the domain. The domain of that function would be negative infinity to positive infinity. Finally, we have f divided by g of x. So f divided by g of x would be f of x divided by g of x, meaning that we would have a rational function, x squared minus 9 over x plus 3. Now here, before we do anything else, we should realize that negative 3 is not allowed to be in the domain of this function, because if negative 3 is in the domain, then we have division by 0. Okay? Right here, we should realize that x is not allowed to equal 3. Okay, we talked about that earlier in the chapter. Now when we reduce this, however, the top factors, because it's a difference of two perfect squares, into x plus 3, x minus 3. And then the x plus 3's cancel. So what does that mean? That means, or it can't be negative 3, sorry. That means that there is a removable discontinuity, or hole, at x equals negative 3. As for the function itself, it would simplify to x minus 3. So f divided by g of x is x minus 3. However, the domain of this function would not include negative 3. So it would be negative infinity to negative 3 and negative 3 to infinity. Okay, so there would be our f times g, our f divided by g, and the related domains of those two items. Same with f plus g and f minus g. Again, the reason we're bringing up domain is because these ideas of domain and range and how to locate discontinuity, all of that stuff comes from earlier in chapter 1, and you are still expected to remember it here in about a section and a half, about a week and a half, when we hit that chapter 1 test. All of these types of questions would be fair game. So we need to make sure we remember how to find domain, how to recognize discontinuity, how to classify discontinuity, and how to write out domain intervals in interval notation. Okay, next up is another type of operation we can carry out on a function, which is called composition. Sometimes what we do is we take the x value, the input for a function, and when we get the output, we'll actually take that output and make it the input for another function. So we'll take the answer from f of x and plug it into g of x, or vice versa. Sometimes we can even plug it into the same function again. So there's two different ways to write that. That's called composition of functions. And that's g of f of x. This little open circle here means of. Okay? Or we could write it simply with just function notation, g of f of x, as written on the right. Either way, we're going to start on the inside and work our way to the outside, which means we're going to evaluate f of x first, and we'll take f of x and plug it into g of x. Okay, so both of those notations are exactly the same. So here in example 3, we have an f of x and a g of x functions provided in the directions, and we're asked to evaluate various function values. So if we want to find f of g of 3, first of all, we need to remember that that could be written as f of g of 3 as well. That means the same thing. So if what we do first is we find the value of g of 3. Now we've done that many, many times. We should know that we're supposed to plug that in for x in g of x, which would give us a value of 9. Then to find f of g of 3, all we need to do is plug 9 into f of x. So we take the output from g of 3, which was 9, and we plug it into f of x. That gives us a value 9 minus 5, meaning that f of g of 3 is 4. Okay, on example B, same idea. We're going to do f of 3 first. So we plug 3 into f of x to get negative 2. And then we do g of f of 3, which is really g of negative 2. meaning we're going to do negative 2 squared. So g of f of 3 is positive 4 as well, coincidentally. Completely coincidental that it is the same answer, okay? We feed one into the other, okay? We take that value, negative 2, and we plug it in for f of 3. Okay, we can do the same thing with two straight functions. We can do f of 3, which is the inside. That would be 3 minus 5, which we just said was negative 2. And then if we want to find f of 3, well, that would be f of negative 2, which would be negative 2 minus 5. So f of 3 would be negative 7. And remember, that could be written in either notation. In fact, I'm regretting not writing that notation on the second example, so I'm going to add it there as well. Okay, this could have been written as g of f of 3, which was 4. Okay, so on to example D. On example D, we would start with, remember, it could be written as g of 3. So we do g of 3 first, which would be 3 squared, or 9. And then to find g of 3, we're going to actually find g of 9. Because g of 3, this value here, is 9. So plug it in. So that would be 9 squared, meaning g of 3 is 81. Okay, now that can get a little bit more complicated when they don't give us an actual value to evaluate, but instead ask us to plug in a variable expression. So f of g of x. Well, g of x is given in the problem as being x squared. So if they ask us to do f of g of x, that's really asking us to do f of x squared. Now, we should have plenty of experience with that sort of stuff from Algebra 2. What we're supposed to do then is evaluate f where we plug in x squared for x. Well, that would just be x squared minus 5. We can't simplify that, so that would be our answer. Okay? Now, remember, that could still be written in the other notation. That could be written as f of g of x would be x squared minus 5. Okay, finally, for the last one, we would start by doing f of 2x, which means we're going to plug 2x in for x in f of x, which would be 2x minus 5. Then to find g of f of 2x, we're really going to be doing g of 2x minus 5. So g of f of 2x would be 2x minus 5 squared, because we'd be plugging that binomial in for x in g of x. Now be careful with that. Remember that when you square a binomial, you're really foiling it times itself, which means we would need to multiply that out and then combine like terms to get our final answer for g of f of 2x. So g of f of 2x would be 4x squared minus 20x plus 25. So 4x squared minus 20x plus 25. And again, remember, that could have been written g of f of 2x. That means exactly the same thing. Okay, so example 4 is more of the same with some more complicated functions, and I believe that example 4 is the last part of this note, and it is. Okay, so when we want to do f of g of 6, we do g of 6 first. Remember, this could be written as f of g of 6. Okay, so do g of 6, which would involve plugging a 6 in for x in g of x. So g of 6 would be 12 plus 3, or 15. Then we do f of g of 6, which would really be f of 15, which would be the square root of 15 minus 5, meaning that f of g of 6 is the square root of 10. That does not reduce, so that is the final exact answer for the value of f of g of 6. Okay, on the next one it asks us to do g of f of a. Remember, that could be written as g of f of a. So first we would do f of a. Well, that's as simple as rewriting f of x, only instead of an x, we have an a. So that would be the square root of a minus 5. We would then take that and we would plug it into g of f, which means we're doing g of the square root of a minus 5. So everywhere there is an x in g of x, we're going to plug in the square root of a minus 5. So that means that g of f of a would be 2 times the square root of a minus 5 plus 3. That cannot be reduced, and that is the final answer. Okay, make sure you note that the square root there ends, okay, after the 5. Okay, finally, f of g of a plus 3. Remember, that could also be written as... Okay, so we start with g of a plus 3, which would be 2 times a plus 3 plus 3. Distribute to get 2a plus 6 plus 3, and then combine like terms to get g of a plus 3 is 2a plus 9. So then f of g of a plus 3 is really saying f of 2a plus 9, which means that we are going to plug 2a plus 9 into f of x in the place of x, which would be the square root of 2a plus 9 minus 5. We would combine those like terms to give us our final answer of the square root of 2a plus 4. Okay, so that does it for the basics of composition and function operations. There are going to be 2 additional videos for this section. The next video will go into composition in much greater detail, and then the final video will sort of do more examples of both composition and function operations, addition, subtraction, multiplication, and division, as well as talk more about domain. Thank you very much for your time and attention.